So, dear participant, today we are going to discuss a very important topic that is called Introduction to Design and Analysis of Experiment. So, maybe you have heard about the term design. Let me share my screen to all of you. Okay. So, this topic, that means design and analysis of experiment, in which we will not only talk about what designs are, we also talk about that after discussing about the importance of design, we will also discuss that how to do the analysis using various methods that we have in the course design analysis of experiment. So before going to start the topic, I want to recall that why we are using statistical tool. So let me take you to that part. So we know that statistics is a subject that is used to extract information from the dataset, and we can analyze the information using various tools, right? So statistics is further segmented into two further branches. One is called descriptive statistics, and the second one is called inferential statistics. If you're familiar of the term descriptive, then it is very good because today session will not discuss about descriptive statistics, but for those who are not very much aware about the term descriptive, I want to spend some time for them to explain this topic. Descriptive means, so we know that we can only extract information from the dataset that we have with us. So when any small, or you can say any dataset that is given to you, so it may possible that that dataset will be related to some sub part of the population. So here population means that corresponding to a particular objective. So we are only considering some observations of the population. So why I'm saying that this is subpart, why this term is different from the sample term, because in the sample we try to take observation from different you can say directions, or you can different scenarios, so that we try to uh, explain, we get more information about the complete population. But when I'm saying subpart, it means that I'm only referring to one part. Okay, so I'm not referring to the rest of the part here. Okay, it may possible that this information was only available to you, and you have to just make statement about this part, and the researcher is not concerned about the rest of the you can say observation that is not available to him or her. So when we have when we have information that is related to this subpart, and we just want to summarize that one. Okay, for example, if there is a school in which students of 10th grade, okay, the number of the students are you can say 50, and we our main objective is to see that how much marks they are scoring in mathematics or statistics or any you can say course. So our main interest is only to observe the marks obtained by this 50 students of 10th class in a particular subject, and I want a single value that represents the marks of the student. So we know that there are various measures given in the literature like mean, median, and mode to help you to get more uh, exact, or you can say representative value information, because all these three, mean, median, and mode, they give you single value, and we just want that single value will represent the whole population, right? So now we also know that the researcher is not interested about the marks of different schools or it means students of different schools, those are studying in the 10th class. So if our objective is only to study the marks obtained by the 10th grade student of a particular school, then we only concerned about descriptive statistics. That means whatever the tools, methods we have in the literature, they are just help you to give you representative value of this data set only, this one. But now in real life, what happens is we have very bigger objective. So let us suppose the objective can be related to a complete state, can be related to a particular state in which there are several districts also, right? So we want to do a study at state level, but the reason is that we know that it is not feasible, or it is not physically possible to go to each and every individual of a member of the state and get information from that. So what we generally do is we collect samples. We can collect samples. Now here the sample are taken from different districts. Okay, by using some statistical you can say tools or methods that help us to make a clear statement about the whole population. Okay, so hope the idea is clear, but here in the descriptive statistic, we just have one information, one data set is given to you, and our interest only lies in that whatever the information that we have, we just want to summarize that information. But in the and we know that there are various methods available in the literature to help you to summarize the data set. But in the inferential statistics, what we have is we have a very vast population, but uh, the, it is not possible to collect information from each individual. So what we do is we take a sample, and based upon the sample, we want whatever the information we got from the sample, we want to generalize that one, right? So now inferential statistic is further categorized into testing a hypothesis and estimation. So now there are two ways. Using those ways, you can extract the information from the sample and generalize it to the whole population. The first way is that you can make an estimate. That means whatever the information we have from the sample, what we can do is you can say that the sample values. Okay, let us suppose if I want to derive the mean from the sample observation, I can say that this sample mean can represents the mean for the whole population. So I can approximately say that this sample mean will be equivalent to the population mean if whatever the information I have from my sample mean that remains equal to the population that we think that is equal to the population mean. Okay, so in this, there are various methods, means tools or techniques we have that how to do estimation, which method is more appropriate. So we have certain criteria that is available to us, and based upon that, we can find out a best estimator that can represent the population parameter. So the next second is a testing hypothesis. So now here, what we do is we frame a value of the population parameter. So here mu is the population parameter, and I'm assuming that you are very much aware about the term mu and sigma because in design analysis of experiment these terms are most widely used. For those who are not aware about, I'm going to spend 1 or 2 minutes to explain it. Mu represents the population parameter and it is a mean of the population, and sigma square represents the population variance square. So what we are doing here is we are testing, we are making a statement about the population parameter mean, and we have to verify that whatever the statement we are making regarding the population parameter mean, that is correct or incorrect. Okay, so we have some certain steps or certain criteria that we will discuss, because I will first explain the topic of design of experiment. Then I will also explain to you how to do the analysis of the design that we have considered for the observations. Okay, so as I already told you that in this testing of hypothesis, we not only consider that we not only consider the statement about the population parameter, but we will also discuss how to do the testing. That means how one can make, how one can uh, implement different tests. Okay, and based upon the outcome of those tests, how we conclude that whatever the statement that we have made regarding the population parameter, that is correct or incorrect. Hope the idea is clear to this stage. Once again, I am going to repeat that in the inferential statistics, we have sample observation, and we want to generalize the result or output that we have from the sample observation for the entire population. For that, we have further two cases. The first case is estimation, in which we just whatever the sample values, as you can say, tools we got, so what are sample measures we derive, we are just saying that these uh, functions represents the population parameter completely. But the second step is that second, you can say, different criteria. Another opinion is that we are making a statement about the population parameter, and based upon the sample observation, we want to clarify, we want to test whatever the statement we have made regarding the population parameter, that is correct or incorrect. All the ideas clear. So okay, so now to go ahead with the topic that we have today to discuss with, that is design as an experiment. So let me tell you what is the meaning of experiment. So in real life, when we conduct an experiment, means that we to achieve some, we can say, goal, we keep on trying to do the same task again and again. Okay, for example, if I will take an example of a very small boy, and he wants to play some, he wants to put a ball in some hole, right? So and we can easily see that when you were child, right? So we used to play a lot of games in which we we did not stop till the time we are not able to do a particular type of operation, or you can say we can do some type of task. So here you can see here experiment in engineering sector. We also conduct a lot of experiments so that we will get more accurate result as much as possible. So experiment is a test or series of tests. Okay, the definition is very much clear to you. The experiment is a test or series of tests. So experiment are widely used in the engineering world. What are the reason why we use experiments? The first is process characterization and optimization. So, for example, you are preparing some, you can say, material, right? And you want to cross check whatever the material, raw material that you have used, because you will prepare a material from a raw material. So, it sometimes the composition of raw material varies with time or with expertise, right? So we want to, with experiments, we want to see that the process characterization is good enough, and whether we can able to find, or we can able to get optimization of the same or not. Second is evaluation of the material properties. So again, we want to see that if we change the composition of one material, how the properties of the final material got changed. We will also observe that with the experiment that product design and development. That means if we change the design of the product and what are the steps and what are the outcomes that we observed after changing the product design, and how much time and it means efforts will be needed for the development of the new product. Because we have changed the design, so it may be possible that after changing the design, so we may be required, we may require more time for the development of the product. So the fourth is component and system tolerance determination. So we want, so for example, if you want to test that how much durable your electric switch is, so what we do is we keep on um, keep it on and off on consistently basis. So we want to cross check whether it's a good quality or bad quality. So it may happens with the electronic goods. So to check the reliability or durability of an item, we keep on shutting it on, or you can say shutting it off or on, so that we can see that whether the component work in appropriate manner after getting it on and off, right? So all experiments are design experiments. Some are poorly designed, some are well designed. So why we are saying that all experiments are design experiments, some are poorly designed, some are well designed. The reason is that so when we have a final product with us, so the functioning of that product depends upon the, or it means how the manufacturer has developed that product, and the development will consist of different types of designs. So it may be possible that whatever the item that we are using, that is prepared by a manufacturer that has taken ideas from very, you can say, not very intelligent person, not very experienced person. So maybe it may possible that the final product will not work efficiently for long duration. It will only work for shorter duration. So it may possible that if the person will be from very strong academic background or well experienced, then it may possible due he has given a new idea how we can build a product with the new technique and new design. So maybe with the same raw material, the person uh, can develop more reliable, durable product. Okay, because with the change in design, the functioning of an item got changed. That's why it is said that all experiments are design experiments. Some are poorly designed, some are well designed. So I have taken one example of engineering experiment. So you can see on this right hand side figure that is shown here. So, so for the construction of any item, we have different steps. The first step is we require raw material. That is called inputs. Okay, and we know that after getting inputs, now the inputs can be raw material, it can be inputs of the labor, because it may possible that for the production of any item we need require a lot of resources, like resources of raw material, resources of labor, resources of capital, right, from economic point of view. So in the process, so there are some factors that can be controllable. For example, if we are preparing a cake, right, we need raw material like you can say raw material like maida, or you can say cream. We need raw material like milk, whatever the component that is required for the preparation of cake. But we also need expertise of the person. If the person is well experienced in making cake, then it is going to be very much easy task for that person. But if the person is not very much experienced, then you are not sure we that a person whatever the output we got from the person, that is good enough or bad enough. So now we know that Now, while processing, right, while making a cake, the person can control the temperature, the person can control the humidity of the room. No, I'm not saying that open environment. I can say that the person can control the humidity that is present in the room. Okay. So, but there are some external factors like that is not under the control, right? For example, it may possible that due to you can say uh, breakdown of an machine, the whatever the item the person has prepared that got rotten. That means that got completely waste because there are some factors that can one cannot control it. So those things on which human cannot do anything, human beings cannot interfere. So those factors are called uncontrollable factor. But when there are factors that can be controlled by the human being, those comes under controllable factor. So at the last stage we have output. So when a raw material with expertise of operator gone through the stage of processing. So whatever the outcome we got, that is called output. So experiments are very essential because they want to conduct these steps again and again to see that from where we are getting variation in the final output. And if there is any variation they have in the final output, they want to identify it. And after the identification of the variation, they can categorize where that variation come from the controllable factor or uncontrollable factor. If the variation is coming from the controllable factor, they can remove it because we know that controllable factors variation are those variation that can be controlled by the human being. But when any variation that is coming in the process due to uncontrollable factor that they cannot remove it, so they either they have to bring to the another solution for those things or they have to keep it as it is. So in the engineering experiment, what we our main objective is that how one can reduce the time to design, develop new product and processes, how one can improve the performance of existing process. Okay. So how one can improve the reliability and performance of the product, as already discussed with you. So achieve products and process robustness. So why this thing is important? For example, if you are using any automobile, right? The purpose of buying automobiles is we want to travel. It means we want to go from one A place to B place. So that's why we want to use automobiles. So that will be very convenient uh, thing that helps you to travel easily. But sometimes it happens that what are the automobiles that you're using that may not be you can say that may not take you from one place to another easily. It may break down in between. So that's why they want that whatever the component they produce from the manufacturing unit, that should be robust one. That should do the daily whatever the task that they have to perform. Those tasks should be done by those products. So evaluation of material, as already discussed with you. So it may possible that whether you are getting the output bad due to you can say poor quality of raw material, poor knowledge of the operator, or it may be due to any other reason. So evaluation of material design alternatives, setting components and system tolerance, and etc. So this is the reason. So you can see here is so whatever the things that that are essential and whatever the things that can vary that can bring variation to the final output, one has to observe it, or if it is possible to remove those variation, then one has to remove it, otherwise one has to find alternative solution for those. Okay. So for that, what is the important thing one has to keep in mind, that planning, conducting, analyzing an experiment. Okay, so here you can see is that how one can do the planning, how one can conduct, and how one can analyze an experiment. So for the planning, we know that if someone wants to prepare new raw material, not raw material, you want to prepare a new product. Okay, so our main objective is how one can recognize that which type of item one wants to prepare, and one must be clear about the statement of the problem. Statement of the problem means that if our objective is to improve the performance, so our statement of the problem is how one can improve the performance of the you can say machinery item. But if our objective is to prepare new material that is not manufactured by anyone else, then what design is possible for the construction of that item? um, how one can prepare those items. That means you have to think from the ground level that uh, which thing can do such operations. If you have some idea in your mind, then how one can prepare it, what are the steps, what are the things one has to keep in mind by preparing those things. So after that, what are the factors or levels one has to keep in mind while developing that product? So which one is your response variable? That means if you want to see the performance, if you want to observe that whether whatever the component that one wants to prepare, so which one can be considered as a response variable. Based upon that we can identify that this product is performing well, and whether the product is of good quality or bad quality, and how one can identify that by using this new product your efficiency has increased, right? So how one can test it? For that we need one variable that is called response variable. And the fourth is choice of design. So choice of design are very important, that how one can prepare such a design that is more efficient. Okay, so it is possible that with experience, with the discussion, or with brainstorming, one can choose a design that is as per the requirement of the objective. So now we have the design. We know that which one is our response variable. We know that what are the factors or levels and what range they take. So based upon that, and one can start conducting the experiment. Okay. So after conducting the experiment, we know that whatever our input variable, we know that how to do the processing. So the last thing, after doing the processing, we got as an output. Now the next step is we have to note down the values of those output, and the next step is we have to implement our statistical analysis over the output values. And from the statistical analysis, we have to draw conclusions. So we have to say that whatever the statement, whatever the objective that we have kept in our mind, that using this new quality of product will help us to increase you can say increase the satisfaction level of the customers, increase the efficiency of an item, so whether that task is fulfilled or not. So based upon the output of statistical analysis, we can conclude, we can draw a conclusion, and we can make recommendation that this type of new experiment, this type of new design, this type of consideration of new factors or levels, whether those things are helpful or not. So, in the continuation of planning, conducting, as an experiment, so what are the main things that we have to keep in mind? So, you can see that. So, we not only have to consider from the statistical point of view, we also have to consider from the non-statistical point of view. So, get statistical thinking involved early. Okay. See, these are the primary steps that one has to keep in mind. So, your non-statistical knowledge is crucial to success. Why it is so? Because if any person you can say, just have only statistical knowledge, so for example, the person who are not aware about the domain in which he is working, then he just work with the numbers, and sometimes it happens that whatever the conclusion we got at the final stage, those are meaningless. So it is essential that the person who has no prior information of the domain may ask any any person who has some expertise in that area. Okay, and then from that uh, suggestions of that person, one has to make a clear statement, right? For example, you can say that if the person uh, wants to study that uh, whether the component, it means whether different components of uh, s- strengthening the quality of alloy wheels, right? So if the person has no information that which components can help to increase the strengthening of the alloy wheel, he just only aware about the data set. So but the person who has some prior information or prior knowledge that which component is beneficial for the strengthening of the alloy wheel. So using number one can draw any meaningless conclusion that this component uh, is beneficial or this component has no you can say importance while for the strengthening of the alloy wheel. But actually that component and other component are very much important for the strengthening of the alloy wheel. Then based upon the numbers, one can make different conclusions. So it may be essential or it is always recommended that one should also have to incorporate non-statistical knowledge while doing any analysis of the design. Okay, so statistical knowledge is essential, but non-statistical knowledge is also essential. The next thing is think and experiment sequentially. So it means that for example, if we are conducting an experiment, before conducting an experiment, one must has to visualize that how one can do the experiment, how one can collect the information, and after getting the information, how to do the analysis, and what which tools can be used for the analysis purpose, and how one can draw the conclusion. Okay, and then one has to start the experiment, because if one has no clear idea that how to conduct the experiment, then one cannot draw the conclusions simultaneously. So we were discussing about one example in which you can see that in this example we have response variable yij, y1j and y2j, where y1j represents the values corresponding to modified motor, and there is another variable that is called y2j in which we have values corresponding to unmodeled unmodified motor. So basically, the objective of this study to see that whether tension bonds strengthen data for the Portland cement formulation experiment. So they have two. There are two factors: modified motor and unmodified motor, and they want to observe that whether there is any significant difference between these two groups or not. Okay. So now, if you want to see just from the observation that how these observations are uh, deviated from each other, what so, so for that we have very simple diagram that is called dot plot, in which you can compare the observation corresponding these two factors simultaneously. One, the value corresponding to modified motor are shown first, then the values corresponding to unmodified motor are shown after that. And you can see that the deviation for the modified motor is on the lower side. Means there are more values corresponding to modified motor, that values are very less. And for the unmodified motor, we have very high values as compared to the whole data set. Okay. So when we will derive the mean, because I have already discussed with you that there are some tools that helps to summarize the data. So here we can see that if we derive the mean of the first variable, that is modified motor, so we got the value of 16.76 that lie here, and corresponding to second a variable in which we have values corresponding to unmodified motor, the value the mean of those observations are 70.04. Okay, so now here you can see that it can be seen that there may be some difference between these two groups, but to observe the actual difference we have other tools also, like one can also draw histogram. Okay, histogram corresponding to a variable that help us to see that what is the, you can say, shape of the observation. So from this graphic representation, one can see that although the data set is taken from different case, but this is just a graph. This is just for the illustration purpose, that when we have any data set and how one can represent the data into graphical manner. So coming back to that example in which we had two variables, one is modified motor and second is unmodified motor. There's a one another method that is called box plot. So I want to spend some time because this box plot, that means some of you may not aware about the term box plot. So you can see that box plot is a very, you can say, most widely used tools nowadays. So that helps us to compare the data set, different variables on the same platform. So you can see that this is the box plot corresponding to modified motor, and this is a box plot corresponding to unmodified motor. As from the dot plot, we also observe that the values corresponding to unmodified motor are, means they used in that variable, the observation values are very high as compared to unmodified motor. Okay, so that's why this basically the full name of box plot, box and whisker plot. So these lines are called whiskers. Okay, so now here, what is the purpose of this line? This line show that what is the minimum value the data set has taken. Okay, and this is the maximum value the data set consists of. So this box, from where this whole box starts, this is the first, you can say, line. That means if I want to construct a box, I can say that this is the first line of the box. So this value correspond to quartile one. Okay, so I'm going to also explain what is the meaning of quartile one. Okay, if someone is not aware about this, the definition of quartile. So this value corresponded to value of median or quartile two, and this line show the quartile three. So quartiles are basically those measures that divide the whole data set into four equal parts. For example, I think all of you have heard about the term median. What is the purpose of median? Median divide the whole data set into equal parts, right? Okay, so whatever the values we have below the median, that covers 50% of the area. Okay, so it means there are 50 observations that are less than this value of median, and there are 50% of the observations that are above this value of median, right? So here in the quartile, what we are doing, we want to split. We are splitting the whole data set into four equal parts. So it means that, so the first part, after divide, it means the first part will consist of, you can say, 25% of the data set. That means this section. The next section will consist of 25% of the data set. Then third section will consist of 25% data set, and the last one is remaining 25%. So here you can see that. So when I combine these two sections, that is 25%, 25%. So this will be equivalent to median, because the total observations covered till this stage is 50%. So this is called M or Q2. Okay, both have the same meaning. And when you club all these three sections, 25%, 25%, 25%, then it will become 75%. Okay, so this is called Q3. So here you can see that this value Q1 shows that before this value, we have covered 25% of the observations. And from Q1 to Q2, This shows the 25% of the observation. And here again, this value Q2 to Q3, it shows 25% of the observation, and the remaining 25% are shown through this whisker plot, whisker value. Okay, the idea is clear. And now the thing is that how we can make comparison between two box plots. The answer is, you can see that here the box is very wider enough as compared to this box, so it shows that we have higher variability in this variable values as compared to this. Although the whisker values are very you can say the line whisker lines are very long as compared to here, but uh, we are more concerned about the it means length of the box. If the box will be of high length, then it means there must be some variation that lies between this Q1 to Q3. So if the whisker length is very high, then we can see that there are more observations that lie in this. That means there is a lot of variation that lie starting from this point to this point, if I'm talking about this thing. And here we can see that the length of the whisker is very small, then we can see that there is a very less variation in the last 25% of the section. That can be easily visualized from this dot plot also, that the value of uh, unmodified variable starts from 16 point something close to 16.5 55 or something. And here we can see that there are three observations that are very close enough, so that means that the variation is very less here. So here you can also see that the variation starting from this, that means if we consider this observation that lies at 60.52, and we have one observation that lies at 60.90. So obviously the variation will be very high among these two observations. Now, when I'm talking about the term variation, it means that I want to observe the variation of this observation from its mean value. So the difference will be it means because uh, we are observing the variation corresponding to sigma square. This is the one measure in which we observe the variation of each observation. That means this observation, if I am assigning as xi from its, or you can say y1 I from y1 power. So we can, when we have most of the values that deviate a lot from its mean value, then we can see that the variation will be high. So that's why I'm saying that this value is very far away from these values, are very far away from these values. So it means that the mean is although 60.76. So if any value that is very far away from this mean value, that means automatically our variability is very high in this data set. Okay, and one can also observe from the box plot that the range means the lowest the range means high difference of highest value minus lowest value when it will be very high. Okay, then it can be easily be observed from the box plot that this data set, that means the values corresponding to this modified variable is may not be equivalent. That means there must be some significant difference in the mean value. There must be some significant difference in their variability. So can we say that this data set, that means the data set corresponding to modified, is statistically significant different from the unmodified variable? So for that, we have to implement some test on the data set. From the graphical point of view, we can say that there can be possibility that these two data sets are statistically significant. Okay, that means it can be different, but we have to prove it statistically. For that, we have to implement some test. Okay, so I already discussed with you that in this inferential part of statistics, in which there are two categories. One is called estimation and testing of hypothesis. Okay, so here you can see that here you can see that we are now going to implement this method. We will do this hypothesis testing. That means we will construct the hypothesis, and based upon the hypothesis, we will try to make a conclusion whether the mean of those two groups, mean of the variable of this modified and unmodified, whether they are statistically significant different or not. Okay. So for that, we will implement the technique statistical hypothesis testing, the useful framework for many experimental situations, as already explained to you. So origin of the methodology that starts in 1900. So we will use a procedure known as two sample t test. So why we are only using this method? Let me tell you some reason behind that. Okay. So for the conducting of testing of mean in the literature, there are some tests available. Okay, so the first criteria is that we are testing for two mean of two groups. Means I am making assumption that the mu1 represents a mean of the population, mu2 one population, and mu2 represents a mean of the second population. So here population means values corresponding to one variable. Here we can assume that the mean of the variable corresponding to modified or unmodified, and the second one is vice versa. Second one's the other one, or vice versa. You can whatever the group you will choose as first. That means you can choose modified first, you can choose unmodified first. But the main thing is our main objective to see that whether these two groups are statistically different or same corresponding to the mean value. Okay, so for that we have some assumptions. The first assumption is that the data set for normal distribution. So normal distribution means that we want our the shape of the data set to be a bell shape. Okay, and if it is more than 30, then it is it can be say that if the shape of this data set is bell shaped curve and we have more than 30 observation, then we have one more information that is called value of population parameter sigma square is given to us, and sigma square means that if the value of sigma 1 square corresponding to first population, and the value corresponding to sigma square corresponding to second population is known to us, and they are also equal. Okay, these values are known to us, and they known to us, and we can go with the jet test. Let me again help you to understand. So the first objective is that if we want to make comparison of mean of two groups, the first requirement is that our data set follow normal distribution. Okay. Okay, and the second criteria is that we have the values of the population parameter variance. Okay, then we go with the jet test. But the problem is that when we are doing any study, it means when we are conducting any uh, experiment, so we do not have the actual value of this population parameter sigma scale. Okay, so in that case, so we have another test available in the literature that can be implemented uh, while considering the first assumption that we need our data set should follow normal distribution. Okay, and there is no such criteria that whether the observation are more than 30. We just want that our data set follow normal distribution, and if it follow normal distribution and the value of the population parameter sigma is not known to us, but the only assumption we need is that they must be equal. So although they are unknown to us, but we assume uh, that they must be equal to each other, then we go with the test that is called t-test. Hope the idea is clear. Let me again recall. So for the testing of mean of two groups, the first requirement is that our data set for a normal distribution. Okay, but we also need that we have the values of the population parameter that is called variance. But if but generally we do not have the values of variance. That means the population parameter variance. So in that case, we have another test that is called t-test that can be only be implemented with the assumption that our data set should follow normal distribution and whatever the variance parameter, that means of the population. Okay, it can be the sigma 1 scale corresponding to the first population, sigma 2 scale corresponding to second population. They must be equivalent, then we go with the t-test. And if we have very strong evidence that the population parameter sigma 1 square is not equal to sigma 2 square, then we have another modified form of this test that is called Welch test. That is basically a modified version of t-test. So I'm going to discuss them one by one. So as already discussed with you, that there are some requirement, and based upon those requirement we can implement our test. The first requirement is that our dataset should follow normal distribution, as already explained. That normal distribution means the bell-shaped curve distribution. And in the theory of normal distribution, so there are two parameters. One is called mean, mu1, and second one is called sigma square. I'm not going to discuss with the mathematical part, but let me try to keep it as simple for you so you can understand the whole logic. So as already discussed with you that we have sample corresponding to this factor, that is, now in our case we can assume that it is corresponding to modified and second one is corresponding to unmodified, right? Or you can keep this as unmodified and modified. Okay. So the first requirement is that data should coming from normal distribution, and we are making such type of statistical hypothesis. The first hypothesis is that we null hypothesis, and in this null hypothesis we always assume that this population parameter mu, the mu or mean, they are equal for both the population. That means we have this assumption that the mean of the two groups, they are equal under this null hypothesis. So this is called null hypothesis H0, and this is called alternative hypothesis H1, in which there may possibility that you can assume that mu1 can be greater than mu2, mu1 is less than mu2, but here we are making assumption that mu1 is not equal to mu2. So when we have this assumption mu1 is greater than mu2, then it is called one-sided test. Okay, mu1 is less than mu2, then it is also called one-sided test. But when we have this alternative hypothesis, mu1 is not equal to mu2, then it is called two-sided test. Okay, as already discussed that because we are dealing with sample observation, so we have to estimate the population parameter, and how you will get the values of uh, sample mean and sample, you can say standard. Uh, I'm using the term uh, sample variance, okay, because we are deriving the variance from the sample observation, and we have assumed that the sample mean is used to estimate the population parameter mu, and here sample variance is used to estimate the population variance sigma square. So now, using the above formula, although we have discussed that the mean of the first group was y1 bar 16.76, as already shown on the dot plot, or from the box plot, you can see this one. And this is the mean corresponding to the second variable, that is unmodified. Okay. So we have derived S1 scale by putting the values of yi in this formula and then taking the deviation. Okay, here we are taking the denominator as n minus 1, because the reason is that if we consider the denominator as 1 upon n, then from statistical point of view I'm saying that in the literature we have proved that what this estimate is called bias estimator. Okay, while considering 1 upon n minus 1, so it will become unbiased. Okay, this is relevant for those who are studying this topic from very in-depth point of view. So I'm discussing these things simultaneously. So here, when we take the square root of this S1 here, so you will get value of S1 as 0.316, and we have 10 observations in both the cases. So similarly, we have derived the mean for the second group. Then we have derived the sample variance. Then we have derived the standard deviation corresponding to the second variable. And now, as already discussed with you, that how this t-test works. So we have a general criteria. The general criteria is that we will take the difference of the mean of the two groups first. Okay, so you can see that the mean of the first group is 16.76 and the mean of the second group is 70.04. So we will take the difference first, and we will take the standard deviation of the difference in the sample mean. Okay, so here uh, I'm going to tell you that although the term is written as standard deviation of the difference in the sample mean, so we have a formula that when we derive the difference of the uh, you can say difference of the mean, that is y1 bar minus y2, and then we want to derive the standard deviation. The formula is in positive. It doesn't mean that we are taking the difference of sample mean and we want to derive the standard deviation, so it must be negative. It is always positive. Okay, because there are few properties of variance that while taking variance of mean of two groups, it is coming as positive, and under the assumption that they are independent to each other. Okay, so here you can see that we got the formula for sigma square that show the standard sample variance of the difference in the sample mean. So when you take square root of this will become standard deviation. So when I take the square root of this sigma square, that will become the standard deviation of the difference in the sample mean. So the formula suggests that the sigma squares are known to us. Okay, sigma squares are known to us, and we are taking the difference of sample mean. Then we go with the Z test, as already explained to you. So if the variance were known and we could use the normal distribution as the basis of the test Z naught, that for normal distribution 0, 1, and if the two population means are equal, right? So we derive the value of Z naught by using this formula only when the value of the sigma square are known to us. Okay, as already explained to you. Now, how one can make a conclusion, whatever the value we got from here, whether that value is lead us to test the null hypothesis or accept the null hypothesis. So for that, we have statistical tables with us, and we will observe the value of this test. You can say observe the value from here also, and we make comparison between these two values. For example, there are some requirements that, or generally we assume that we are considering 5% level of significance. What is the purpose of 5% level of significance? Let me tell you in 1 or 2 minutes. So you can see from above that we have considered hypothesis that h naught mu1 is equal to mu2, and alternative one is mu1 is not equal to mu2. So here you can see that we are talking about two-sided test, right? And we are making assumption here that we are testing this you can say null hypothesis based upon 5% level of significance. It means that we are excluding 5% or in total 5% area from the left hand side and from the right hand side. So it means 2.5% area on the left hand side and 2.5% area on the right hand side. So whatever the value that segregate, or you can say the divide this probability into two, you can say, into different parts. Okay, the area into different parts, you can say. So this is called ordinate, or we can generally call as a critical value. So I can say that there is any number like 1.96. Okay, at 196, in the case of normal distribution, minus 1.96 is the value, and before this value of 1.96, because we know that the normal distribution take value from -820 to infinity. So value of minus 1.96, before that we have a reason that covers 25% of the area of the distribution. And similarly, we have value 1.96 that covers the, you can say, before after that value of 1.96, we have a area under the curve of the normal distribution as 2.5. Okay, 2.5%. So here you can also see that if someone is not very much confident about how one can derive it, so there is a method one can easily see, that you have to subtract whatever the probabilities are given to you, you have to subtract the values from 1. So we got an answer as 0.0025, 0.025. So what does it mean instead? We have one, you can say, we have value of this test at a 6, that come that before that or after that we have 22.5% area. Okay, so because normal distribution is symmetric, so we can consider that whatever the value we have on the right hand side, the negative part of that value should lie on the left hand side. Okay, so it means if there is a value of x that covers something like 3% on the right hand side, so the negative value of minus x will, uh, before that there must be 3% area should be covered. Okay, so this value of this critical points are very important, because that help us to divide the whole probability area into different sections. Okay, so here we got an information that the value of 1.96 divide the population, divide the this probability curve areas into different sections, and on the right hand side we have some, you can say, proportion. Similarly, we have some proportion on the left hand side, but these proportions should be equal if the critical points are equal. Okay, because due to the symmetry property of the normal distribution. So as already discussed with you that, so if the variance were known, the most important point you have to keep in mind for the testing of mean of two groups, if the variance were known and we have this hypothesis mu1 is equal to mu2, and alternative one is mu1 is not equal to mu2. So we will compare the values of the z naught that we have seen here, with the tabulated value of z. So if the calculated value of z naught is greater than, or you can say that mod of z naught is greater than the value that we have derived, that is 1.96, then we reject the null hypothesis. Okay, and this is called a fixed significant level test, because we compared the value of test 6 to a critical value 1.96, and we selected in advance before running the experiment. So as I told you that we have to fix the value, that whether we are taking 5% level of significance, whether we are taking 1% level of significance, whether we are taking 10% level of significance. Okay, the value of z naught is greater than 1.96, then we reject this null hypothesis. So another way to do this, that is very popular, to use the p-value approach. Okay, p-value approach means that we first derive the probability, that what is the probability that this critical, that means the formula that we are using, this is called test statistics. Okay, what is the probability that this statistics is greater than a particular value? Okay, test statistics is greater than, for example, the value that we derive from here. Let us suppose this is the value of x we got after putting the values in that formula. So what is the probability that we got here. So if we got any value like after solving this probability, we got value 0.10, or you can say we got value 0.001. Okay, so we will check that this is called p-value. We will check that whether this value 0.10 is less than 0.05 or greater than 0.5. So based upon that, we will make our conclusion. If the value of the p is greater than 0.05 and we have assumed 0.05 as our level of significance, then we do not reject the null hypothesis. So it means that whatever the statement that we have made regarding the null hypothesis, that is mu1 is equal to mu2, that is correct. And if the value of the p is less than 0.05, like here you can see, then we are going to make a conclusion that we are going to reject the null hypothesis. That means that whatever the assumption that we have made regarding the two groups, that is mu1 is is e- sorry, is equal to mu2, that is mean of the first population is equal to mean of the second population, that is not valid. Okay, so here find the probability of z naught from the table. So that gives us the p-value, this one. And because we are dealing with the two-side test, so we have to multiply this p-value with 2. Okay, the reason is because we have derived the p-value. For example, in this example, we have just considered the value of z is greater than x. Okay, that is on one side, that is on upper side, right? And as I already told you that if we are considering in the alternative hypothesis mu1 is not equal to mu2, that is a two-sided test. And because of symmetry property of the normal distribution, whatever the critical point we have derived on the one side, that should be equal to the other side. So that's why we multiply by 2. And we can say that, as already told you, that if the p-value is less than the level of significance, in this example, we have assumed the level of significance as 0.05. So we are going to say that this value is less than 0.05. So we are going to reject the null hypothesis. Fine. Okay, so the earlier example that we have discussed, that is only that is done through this Z test, because we have making this assumption that our data set for normal distribution, we have the value of sigma square that is known to us. But if the value of sigma square that are not known to us, then how to do the analysis? So let me read it for you. The t-test, the z-test just described would work perfectly if we knew the two population variance, right? Since we usually do not know the true population variance, what would happen if we just plugged in the sample variance? As already told you that we do not have the value of the population variance given to us. So what we do is we replace the sigma square value with the sample variance. The answer is that if the sample size were large enough, say both n is greater than 30 or 40, the Z test would work just fine. As already explained to you, that for the large sample size and the value of the sigma square are known to us, but somehow if it is possible that the value of sigma square not known to us, still for large sample size, we can assume that the sample variance are almost similar to the population variance. So we can go ahead with Z test for the last data set. But the result that we got from those, you can say test statistics, they are not, you can say, they are not exact result. They are just approximate. Okay, because we are making assumption that our sample variance are equivalent to the population variance, right? But many times that isn't not possible. So what we do is, because when we have very small sample size and but our data sets still satisfy the assumption of normality, then it is better to go with another test that is called t-test. So it turns out the sample size is small, we can no longer use the normal distribution, that is z-test, as the reference distribution for the test. We go with the t-test. Okay, now you have observed that the formula is, you can say that the formula that we have used in the previous test statistics will be of same format. The only difference is that that now we are replacing sigma square with their sample variance. That means in the previous formula of Z naught, you can observe that we have taken difference of mean of two groups. Okay, this was the formula. But in spite of considering sigma square, now we are considering S1 square. Okay, because we do not have the true value of the sigma square parameter. So, but we have one assumption required that these value of sigma 1 square and sigma 2 square, they are equal to each other. So, in spite of writing this S1 square and S2 square, you can also, there is another way to write down by taking their weighted average. So this is called pooled individual sample variance. So what we are doing here is we are taking the pooled average of these two sample variance, and it is denoted by SP square. So we are replacing this formula with this one, y1 bar minus y2 bar, sorry, y2 bar, then SP square upon n1 plus SP square upon n2. Because these two terms are equivalent to each other, we can take it outside. So this will become y1 bar minus y2 bar sp square root of 1 upon n1 plus 1 upon n2. Okay, so this is the way that we have got this form. So now the criteria will be again same, that we first derive the value of test statistics. Okay, and we will compare this value of test race with the tabulative value. But now, in the previous case, we compared the value with the Z table in the previous case, but now we are using T test. So we have to compare the value corresponding to uh, this statistics corresponding to T table. Okay, so value of T naught that are near zero are consistent with the null hypothesis. The meaning is that because if the difference of this y1 minus y2 is very small, if it is coming in terms of 0 0 something, then we can directly be say that if the value of T naught is coming very small, something 0.00, then we can easily say that null hypothesis is correct. Okay, that we are going to accept the null hypothesis. We are not going to reject the null hypothesis. So so we have to make comparison of this T naught value with the tabulated value of that from the T table. So value of T naught that are very different from zero are consistent with the alternative hypothesis. So the meaning is that if the value of this T naught is coming to very high, it can be 5, it can be 10. Okay, and we will make comparison of these value with the tabulative value. And if the value of T naught is greater than tabulative value of T, then we are going to reject the null hypothesis and say that whatever that means there must be some difference in the mean of these two groups. So whatever the alternate hypothesis we have framed, if it is not equal to, then we can say that they are not equal to. If they are written as greater than, then we can say that mu1 is greater than mu2. And if it is written as mu1 less than mu2, then it is mu1 less than mu2. So based upon the value of T naught and making comparison of this T naught value with the tabulative value, we are going to make our final conclusion. So T naught is a distance measure how far apart the average are expressed in the standard deviation units. Okay. So the two sample t-test, as already discussed with you, that one can derive the value of sp square n minus 1 s1 square and n2 minus 1 s2 square. We put the values here in this formula and we derive the standard deviation. And we, after putting all those values, we got this value, for example, minus 2.20. Okay. So the two sample means are little over two standard deviation apart. So is this a large difference? For that, we are going to make comparison. So we can say here is that as discussed earlier, that we have to divide the our probability curve into some sections. This is called critical region, and because we are doing testing on the two-sided Two-sided means whenever we have written our alternative hypothesis as mu1 not equal to mu2, so it is both-sided test. So this is critical reason, right? So we will got this reason by considering, if we consider 5% level of significance, so it means that we are skipping 2.5% here and 2.5% on the you can say left side and the right hand side. So we got a critical values as minus 2.101, right? So here you can see that we got critical value as minus 2.101, but the value we got from the test statistics is minus 2.20. Okay, so minus 2.20 is less than minus 2.101, right? So we can say that that value of T naught lie here somewhere in this critical region, because now we are observing on the left hand side. So in the left hand side, when we're talking about negative values, so the higher the negative value, the lesser. So it must lie on the critical region. Okay, so we can conclude from this comparison that we are going to reject the null hypothesis because our value of test statistics did not lie in the critical region of the test statistics. Okay, so we need an objective basis for deciding how large the test statistics T naught. Okay, and based upon the comparison, we will draw our conclusion. So this is the you can say glimpse of the T distribution. So one thing you have to keep in mind that in the case of normal distribution, we do not have any concept of degree of freedom, but here in the T distribution, we have a concept of degree of freedom. Let me tell you. So when we are using this T naught, okay, we are making an assumption here that this T naught follow T distribution with n1 plus n2 minus 2 degree of freedom. So I'm not going to discuss at this stage at how we got this value of degree of freedom n1 plus n2 minus 2. Just you have to keep in mind that this is the way to make comparison. And what is n1 and 2? N1 and 2 represents the number of observations we have in the first and second group. So you can see that in the first group we have 10 observation, the second group we have 10 observation, and we club them. So we have 20 observation, but we are reducing you can say 2 degree of freedom. So I'm going to 18 degree of freedom, and corresponding to 18 degree of freedom, I want to see the value corresponding to 0.025. So corresponding this, we got value 2.101. So here the value are given on the positive side. So as already told you that like the normal distribution, T distribution is again symmetric. So whatever the critical point we got on the right hand side, if we are doing a two-side test, so the same critical value but with the negative value, you can say negative assigned to it, should be on the left hand side. So we got a value 2.101, and so on the left hand side it should be minus 2.101. So that cover before this value, the area under the curve is covered 2.5%. The area under the curve covered after this value is 2.5%. Okay, so based upon that one can make a comparison. So as already discussed, with the value of T naught between minus 2.101 and minus is consistent with equality of mean. Okay, so it is possible for the mean to be equal and T naught to exceed either, but it will be rare lead to the conclusion the mean are different. So what they're trying to say here is, so if the value of test statistics T naught lie in this region, in this part, okay, although we can make directly conclude that this value doesn't lie in this region, it lie in this critical region. That's why we are rejecting the hypothesis. But anyhow, if any value of T naught, okay, lie in this region, then we can say that we are not going to reject the null hypothesis, we are accepting the null hypothesis. But here, the value of the T naught lie on the left hand side, so that's why we are rejecting the null hypothesis. Now the further is the two sample t test, two sample pool test conclusion from p value. So p value is the area probability in the tail of the t distribution beyond minus 2.20. So we are now deriving the probability. That what is probability? That probability of T naught test status is greater than the value of x. X value means this minus 2.20. So after solving this probability, we got the p-value as 0.042. So as already told you that we have to uh, check this value of p with the you can say level of significance that we have derived earlier. So here it is coming less 0.042 is less than 0.05. So we can conclude that there must be some significant that means there must be some significant difference in the mean of the two groups. So we are rejecting the null hypothesis. Sometimes it is possible that we are not able to derive the exact p-value. So what we do is we make an approximation. Approximation mean here is that we will just see that in which interval our p-value lies. So because we have considered the level of significance as 5%, so if we can say that the p-value is we are not able to write the exact p-value, but we just got this information, the p-value lie in this interval, and based upon that we can also conclude it. Okay, so this is the output derived from Minitab software. There are various softwares available in the market like Minitab, Strata, eViews, and we can also do the we can also solve such problem in Excel, R, SPSS. So this output taken from Minitab. So the idea is always clear from whatever the output we got from different softwares. JMP software is also there. Okay, let me tell you that what is the output that we have from the software. So this is the mean as already discussed earlier that how one can derive the mean. So this is the value corresponding to standard deviation that we can already observed earlier. So there is one value that is called standard error of mean. Let me tell you. So basically standard error of mean is basically when you divide this standard deviation divided by number of square root of number of population, you will get your standard error. Okay, they have derived the difference in the mean. Okay, and they have constructed uh, they have given you the p-value and they have given you the test statistics value as already have discussed earlier. And from the p-value we can easily be observed that the p-value is coming less than 0.05. So we are going to reject the null hypothesis, right? So after implementing this test, so it is also required that whatever the assumptions we have made regarding the test statistics, whether those assumptions are fulfilled or not. Okay, the first assumption is we can only implement a particular test. It can be Z or T. The first requirement is that our data set should follow normal distribution. Okay, the first criteria that generally we say that if the data set is of bell-shaped curve, we can go with a normal test. But actually, if we want to do the testing, then there are various methods available in the literature. The first method is called normal probability plot. Okay, so if the value, that means if all the observation lie on this line, there is a particular criteria how one can construct this line. So most of time we use softwares for the graphical representation. Okay. So here you can see that if most of the observation lie on this line, then we can say that our data set follow normal distribution. And if you want to check exactly whether our data set for a normal distribution or not, so there are various tests available in the literature. You can also use them. Okay, I am naming some of the tests available. Kolmogorov-Smirnov test is there. Shapiro-Wills tests are there. They will test that whether the data set is normal as a null hypothesis and alternative hypothesis whether the data set is coming not from the normal distribution. Okay. So now I'm going to discuss the importance of t-test. So provides an objective framework for simple comparative experiment. So here in the t-test, we can only make comparison for the testing of mean of two groups. Okay. So when we have two factors, two levels, or you can say two variables, and we want to make comparison between them, and our data set for normal distribution and variance unknown, then we go with the t-test. So could be used to test or relevant hypothesis in a two-level factorial like design, because all these hypotheses involve the mean response at one side of the queue versus the mean response at the opposite side of the queue. Okay. So there is one more important concept that is called confidence interval that also supports the conclusion that we got from the testing of hypothesis. So now what we are doing here is that in the testing of hypothesis, we are making comparison of mean of two groups, right? And the alternative one is mu1 is not equal to mu2. Okay, from the confidence interval, there's another criteria that also helps us to conclude from the interval values that whether this hypothesis is correct or whether this hypothesis is correct. So if in the difference of if in the difference of this confidence interval, that means we can say that in this in confidence interval of difference of means of two groups, if we have the value 0 like in this interval, okay, then we can say that our null hypothesis is correct. Let me again repeat. If we have the confidence interval of the mean of the difference of the means of the two groups, right? If we have value 0 lie in this confidence interval, then we can say that our null hypothesis is correct. If there is no value of 0 lie in this interval, then we can say that our alternative hypothesis is correct. Okay, let's take one simple example corresponding to same data set. So here we are deriving the confidence interval by putting the value. That means in this formula we are putting the value of y1 bar, y2 bar, and this value we got from the statistical table corresponding to t, and we have the value of sp. We already know that this is pooled standard deviation. Okay, so we are putting the value. So here you can see that the value starts from negative minus 0.55 and it goes till minus 0.01. So it doesn't have the value of 0, right? And as already discussed just now, so when we do not have the value 0 in this difference confidence interval, we can conclude that our alternative hypothesis is correct. So we can make a statement that there is a significant difference in the mean of these two groups, and these thing can be verified, okay, by testing a hypothesis as we have already done, right? So now there is another assumption while implementing the t-test. Another assumption is that we want the variance of two groups to be equal. Okay, then we go with the t-test, and already explained earlier that if the variance of the two groups, they are although unknown to us, but they are different, then we cannot implement t-test. Then we have to go with the Welch test. Okay, so here we have one data set in which we consider uh, let me read it for you. Okay, nerve preservation is important in surgery because accidental injury to the nerve can lead to post-surgical problems such as numbness, pain, or paralysis. So nerves are usually identified by their appearance and relationship to nearby structure or detected by local electrical simulation. So here you can see that we want to see that after surgery, what are the you can say drawbacks. Okay, so we are observing those things. That means we consider that there are few patients that they are observing such problem, and after doing surgery, normalized fluorescence after 2 hours, what impact that is on the muscles. Okay, so we want to see that whether there is any significant difference among these two categories, nerves and muscles. So we are making uh, test null hypothesis as mu1 is equal to mu2. Okay, and our objective is to see that the normalized fluorescence after 2 hours for nerves and muscle tissue are equivalent or not. Okay, So here you can uh, first check normality of data set. So you can see here from the plot that most of the points, I'm saying why I'm saying most, because there are few points that are not on the line, but still most of the points lie on the straight line. So we can say that they may follow normal distribution. And if you want to exactly check whether they follow normal distribution or not, I already have explained some tests. The one is called KS test, Kolmogorov Smirnov test, and second one is called Shapiro test, Shapiro-Wills test. So here, what we're doing, we are saying that there must be a lot of variation in the variance of the two groups. That means we are not making direct assumption that sigma 1 square and sigma 2 square, although they are unknown to us, but they are equivalent. So for that, we are not going to directly implement the t-test. We are going to implement a modified version of the t-test that is called Welch test. And although I'm not going to discuss with you that how one can derive it, but just for your knowledge, I'm just discussing that for the test, for the testing of mean of two groups, somehow it may possible that the variance of two groups are not equal. Then how to go ahead, how to do the analysis for this? For that, one has to refer to test that is called Welch test. The criteria is same. Whatever the value of test result we got from here, we will compare the value with the tabulated value of the t. Okay, and we can also derive the p value, and based upon the p value we will draw our conclusion. And here from this analysis we got the p value as 0.007. Okay, so one can easily see that there's significant difference between the means of the two groups. Clear? So now the main topic that I want to discuss with you, that we have discussed till now, that how to do the analysis of testing of mean of the two groups. Okay, but in real life it may possible that we have more than two factors, we have more than two levels. Then how to proceed further? So for that, in literature we have one method is available that is called ANOVA, and that also requires assumption that our data set for normal distribution, they have equal variance. Okay, the only difference is that why we implementing ANOVA in spite of t-test is that in the t-test we have two groups, but in the ANOVA we have more than two groups. It can be three, four, five, right? So in that case, t-test does not directly implemented. There are a lot of practical situations where there are either more than two levels of interest, or there are several factors of simultaneous interest. The analysis of variance is the approximate analysis engine for these type of experiments. The NOVA was developed by Fisher in the early 1920 and initially applied to the agriculture experiment. So it is extensively used for industrial experiment nowadays. Okay, the objective is clear that we want to do the testing of mean, but the thing is that we have more than two groups, and we have an assumption that our data set for normal distribution, and they have equal variance, although those variance are unknown to us, but they are equal. So there is a one example in which engineer is interested in investigating the relationship between the RF power setting and the each rate of this two. Okay, the objective experiment likes to model the relationship between each rate and RF power, and to specify the power setting that will give a desired target each rate. So what we have four levels. That means four power level. So we want to make a comparison whether the output corresponding to these four powers, they are equivalent to each other, right? And we have taken five response from each you can say levels. So this is a graphic representation. You can see that uh, we have RF generators, and the output is that means that impact is coming here, anode wafer cathode, right? So the final output is coming here. We want to see that if there is any difference in one component value, whether it lead to significant difference in the final output or not. Okay, so we are taking the example of RF power here. So with change in the RF power, whether it leads to any final conclusion or not, or that means there is significant difference in the final output or not, our main objective is that one. So here you can see that we have four uh, levels of power here, and corresponding to that we have various observation. That is corresponding to power, we have five observations that are given horizontally. Okay, and the totals are already given, and their average also be given. When we draw it on the box plot, you can see that it can be easily be visualized that must be significant difference in their mean value. But we have to test it. Okay, we have to make a final conclusion based upon the statistical test. Okay. So here, what is our objective? Does changing the power change the mean each rate? Is there any optimal level for power? We have to try to find out the answer to such questions. We would like to have an objective way to answer these questions. The t-test really doesn't apply here because we have more than two factors level, right? So we will implement the test that is called analysis of variance. In design analysis of experiment, we have another name that is called completely randomized design. So CRD, completely randomized design or analysis of variance, they are equivalent in design of S DOE, design analysis of experiment, right? So we can see that treatment levels are shown here. This is a generalized method. Observations are there, totals are there, and averages are there. Okay, so we will first observe that how many total observations we have. We have total observation capital N, and how many levels we are discussing, that is denoted by symbol small a, and how many observations we have corresponding to each level, that is shown by small n. It may possible that corresponding to each level we may have different observation. Then it is represented by capital N is represented by summation I vary from 1 to a n I. Okay. When each level has same number of observation, then we write down a times n. So there are two things. One is called fixed effect and end effect. So I will discuss this later. What is fixed effect and end effect? For the timing, our main objective is to do the testing of mean now for more than two groups. Okay. So the name, from the name it suggests that we are doing analysis of variance. Okay. So it means that we are trying to segment our total variability into different segments. I will explain to you that how we will first derive the total variability and in which segment we are going to divide it. Okay, so we have the response wave of Yij here. Mu represents the grand mean, overall mean, and tau I represents the effect that is coming from ith level, ith effect, level that we have. So here we have in the example of each rate, we have four levels. Okay, the first level starts from 160, then we have 180, 200, and 220. Okay, we want to see that whether the value correspond to these level, they are significantly different or not, right? And in each group, we have 5 observations. Okay, so here mu means overall mean, means that we are making an assumption here that values from it means on average all will give the same mean value. Okay, so there is another way to write down Yij is equal to mu plus tau I plus epsilon ij, and we can write down as Yij as mu I if we consider mu plus tau I as mu I. So this is called mean model. So let's come to the final how one can implement, that is very important. The total variability, as already told you, that from the analysis of, that means from the name of the term ANOVA, analysis of variance, we are considering the variance part. That is very important. So as already told you that how one can derive the variance by taking the deviation of each observation from its mean value, because we do not have one single you can say variable here. We have multiple various variables here. To derive the overall variability, we first have to derive the variance of each observation from its overall mean. Then we have to move to the second row. Then we have to move to the third row. Then we have to move to the fourth row. Then we have to club them. That's why the formula for total sum of square is given this manner by considering two summations, right? So now we are dividing this total sum of square into two segments. One is called treatment sum of square and second one is called error sum of square. Okay. So our main objective is to testing mu1 is equal to mu2 is equal to mu a, and alternative hypothesis like we want one group whose mean is significantly different from the remaining group. I'm again going to repeat. Our objective is to check whether there is any one group available whose mean is significantly different from the other group. Then we are going to reject the null hypothesis. Okay. So here, as already discussed, we have a concept of degree of freedom. So total number of observation is an. So the degree of freedom for the total is an minus 1. And the degree of freedom from treatment is a minus 1. And degree of freedom for the error term is a times n minus 1. So I'm going to discuss with you that how we will conclude, make a final conclusion. For that, we need a value of mean sum of square of treatment and mean sum of square of error. So for that, you have to first solve sum of square of treatment. That be the formula that we have written here. We have to put value in this formula and this formula. And when we divide this sum of square of treatment by the degree of freedom and here sum of square of error with the degree of freedom, you get mean sum of square of treatment and mean sum of square of error. And when you take the proportion of these two terms, mean sum of square of treatment in the numerator and mean sum of square error in the denominator, this is called F statistics. Okay. So if the value of the test statistics is higher than the tabular value, then we are going to reject the null hypothesis. So I'm going to repeat the same step that I have just discussed with you. So between treatment, we have the sum of square of treatment as this one. Okay, error term, we got sum of square of error here and minus a. So we got the value of f naught from here and we compare the value of f naught from the tabular value. And we reject the null hypothesis if f naught is greater than the tabular value of f. So I'm not spending more time. The reason is because the criteria is same. We have to solve the test statistics and we have to compare the value of test statistics with the tabular value of the test statistics. If the value of the tabular is less than the calculated value of the test statistics, then we reject the null hypothesis. Otherwise, we do not reject the null hypothesis. Okay. So there is another simplified form of the formula for the total sum of square of total sum of square corresponding treatment and sum of square of error. Okay, because one can easily be derive sum of square of error by subtracting uh, sum of square of treatment from the sum of square total sum of square, right? Okay, so now I'm showing the output. So here you can see that after putting the values in this formula, we got the value of sum of square total as 72,209.75. Similarly, we got the value of sum of square of treatment as 66,870.55. So in the NOVA table, the way is different as compared to test statistics. So T test. Okay, so first we write down source of variability, in which we write down that how much source of variability is coming from the treatment group, treatment, right? Sum of square of treatment. That's why we write down whatever the treatment we have. So we have four levels of treatment. Okay, that is RF power. So the next is sum of square of error. That means the source of variability that is coming from the error term. So let me tell you the difference here is. So we have written this formula Yij mu plus tau I plus epsilon ij. So here the meaning is mu is the overall effect that is coming. Tau I is a means the effect that is coming from the ith level. And if whatever the value that we got from these two values, if they are not able to finalize, to identify the value of Yij, so the reference goes to error term. For example, let me take this thing in more detail. What we are doing here is we are saying that we have one level of this RF power as 160. So we name it as mu1. That means the average corresponding to the values got from this level as mu1, right? So we are saying that mu1 is defined as mu plus tau 1, right? Tau, sorry. So we are saying that whatever the value of Yij we got corresponding to this mu1, okay, we are writing it down as. But there may be possibility that while getting the final output, okay, if we are maintaining a same temperature, same power, so there must be some variation in the final output. Okay, so for example, if we are preparing some material, so if you keep the same power, but still the output varies either with time, with the, when you repeat it again and again. So that variation comes under the error term. I think the idea is clear. So using the same power will not lead you the same value of y response variable always. Will not lead not the same values of yj always. So there must be variation exist between them. Okay. So that variation comes in the error term. Okay. So now what we are doing here in this test, this analysis of variance, we want to see that if there is a variation, that means the total variation segment is coming more from the treatment variability. Okay, but I'm going to repeat again. That means we have total variability here. So we want to see that this variability is coming from the difference in the treatment values, or it is coming from the error term. Okay, so for that, we just take a proportion. We take a proportion of these two variability, and if it is coming more than the objective value, we are going to reject the hypothesis. So this is same thing I already explained to you, that f naught is 66.80, that is less than 0.01. So here from we got the value of test statistics, w calculated value of test statistics 66.80, and this is the graphic representation of f statistics. Okay, w1, and you can see that it lie very uh, very, you can say, on the right hand side. It means the difference is very high. Then only we can conclude that there is a significant difference in the mean of the these four groups, right? So here we have model adequacy checking in the ANOVA. So we are checking the same assumption. Checking assumption is important: normality, constant variance, independency. So have we fit the right model? Because we have assumed that our data set is coming from normal distribution. So we also have to cross check these assumptions. So for that, we first derive the residual part. So what is residual? That is the difference of each observation from its predicted value. Because we have constructed one model, this is the model that we have constructed. So we can say that if we do not know the value of Yij, so we can derive the value of estimated of Yij by putting the value of mu plus tau y. Okay, so we want to see that how much significant difference of this Yij from its predicted value, that is correct. Okay, so we will see that if the residual term follow normal distribution, that is our requirement. Okay, and each observation must lie on this line. We also cross check that our residual plots, they must be scattered. There must be no any pattern exist. So this is the second requirement. Okay, and we have seen that all these things are met here, right? All assumptions. So post hoc ANOVA, it means that it can be implemented whenever we have rejected null hypothesis corresponding to ANOVA. So what is our hypothesis was, so we have assumed that in the previous example we have four groups that mean are equal, and there is at least one group whose mean is significantly different from another group, right? So in the output we got the answer that the mean of at least one group is significant from the other group. Okay, so we want to identify which group mean is significantly different from the another group. For that we go with the post hoc or post ANOVA comparison. So here I'm not going to discuss in detail that how one can do that, but I'm just going to give you that what are the tests available in the literature for the testing of post hoc. The first is called Fisher least square difference and Fisher elastic method that are implemented to make comparison of two groups at a time. Okay, then we start comparison now by taking two groups and compare it whether there is a significant difference between these two groups. Then I will take mu1, mu3, mu1, mu4, then mu2, mu3, and mu2, mu4. And based upon that, we will get the answer that there is one group whose variance is different. So now here, this is just a glimpse I have shown here, that we start making comparison of the first one, two groups at a time. And from the p value, the probability value, we got to know whether they are statistically significant or not. The criteria is if it is less than 0.05 at 5% level of significance. And one can also make a graphical comparison. That means the mean of different groups. And if they are not equal, one can easily see that which two groups are statistically different or not. Now the question is that we have making comparison that we can get the value of response variable yij mu plus tau I plus epsilon ij. Okay, so whether this model is suitable or not, because the question was which model we have to choose. So we have to make different models, and whichever model that cover, that means if our model explain if this is a regression line, so if we can assume that we can consider one more term that is not linear, that means in terms of variable, so that explains the variability in more better manner. So one can also cross check that. So this is linear model, this is quadratic model, because we have taken xk term in the model also. So the reason that why ANOVA works, as already explained, let me recall it again. So in the literature, we have some assumptions here is that whenever we take the proportion of variability of two, you can say, taking the proportion of variability, so whatever the distribution it follow chi-square distribution. Okay. Similarly, when we take the proportion of variability of these two segments, like we have discussed that when you take a proportion of sum of square of treatment and divide by mean sum of square of error, that follow F's distribution. Okay, so these things are important, so one can easily see that which that means if we are taking proportion of these two components, which distribution follows. So this topic random effect model is also very important. Why so? So at the initial stage I have discussed with you that we have random effect or fixed effect. let, Let me tell you the difference between them. Random effect is that effect that means, for example, we have not four or five levels corresponding to a particular uh, component. So we have, let us suppose, 100 levels corresponding to a component, right? But it may not be possible to implement all those levels, okay, and on a particular type of machinery, and then we can compare it. Okay, like in the example of this RF power, so we have taken only four levels: 160, 180, 200, 220, right? So we have noted down five observation corresponding to each level. But if there are possibility that they have uh, temperature 161, 162, and it goes up to 150. So we are not going to check the observation corresponding to each and every level. So it is not recommended, okay, because that may lead to waste of resource and time. So what we do is we take samples, we consider some of the important levels among this whole range, and then make comparison between them. And whatever the conclusion we got from here, that can be generalized to all those remaining levels also. So that is called random effect. And in the fixed effect, what we do is, so let us in the fixed effect, we whatever the levels that we have with us, we implement our analysis only on those levels, and we can't generalize the result for the remaining levels, right? This is the main difference. So in the case of random effect, we have one more assumption is that we also consider this component as a random variable. So that lead to the very some you can say difference in the mathematical format, but there will be no difference in the implementation of robotic. Okay, so now I'm going to take two examples. The first example is corresponding to implementation of t-test. Okay, so in the first example, we have discussed about that we have two groups. Okay, so how one can do the testing? For that, one has to go to, let me take it, data. I'm already put the values in my Excel sheet. So I want to do the analysis corresponding to t-test. So then I go to data analysis. Then I will go to t-test sample assuming equal variance. Right? As already told you what's the meaning. Because we have two independent groups and we are going to do the testing. So that's why I've used t-test to sample assuming equal variance. Okay. When I click, I have to first select the range of the first variable. The range of the second variable. Because we are making an assumption that mu1 is equal to mu2, so I have to put 0 here. And we already have selected the labels. I have to check it. And if I want to show my output on this sheet only, then I have to check the cells where I want to my output. Okay, so this is the output corresponding to t-test from the Excel. And you can see that we got the same mean value that we have discussed earlier: variance, then number of observations, then pooled variance, and we got the same test statistics that we have discussed earlier. And the p-value is coming as 0.042 as earlier discussed. So here we got to know that we are going to reject the hypothesis that there is a significant difference in the mean of two groups, mu1 is equal to mu2. Okay, so this is the hand-on experience of that how one can implement two sample t-test in Excel. Now coming to how one can implement the Nova. So as already discussed with you that we have four levels and we can't implement t-test because that t-test can be only implemented when we have two groups and less than two groups, and for more than two groups we go with the Nova. So how to implement a Nova? First we have to check on this data, then we have to go to data analysis, then we have to select a Nova single factor, click on OK. Then you have to select the range that you have for the observations. So observations are grouped by columns. So we have labels there and we want output on the same page. Click on OK. We can see that we have it shows the count, right? And how many number of observations we have. So what is the sum for those observation, the averages, the variances. Then further we have source of variability like I have discussed sorry, and that so this first row corresponding Nova table shows the variability that is coming from the treatment. This shows the variability coming from error term, and we can see that we have the same F value, right? And we conclude that we are going to reject the null hypothesis. So this is the end of the session. So if you have any query, you can email it to me. So thank you.